Good for you. Good for you.
Any questions? Gets smaller and smaller.
Nobody dropped it, did
At this point, you can't without some, probably the word hospital or doctor has to come into the discussion at this point. All right. Any questions? All right. Describe the way this is turning.
Like which way?
Pardon?
Which way? Or
Like
Yeah.
clockwise or counterclockwise?
If that's the way you want to describe it. Anyone else? Because to me it looks clockwise.
Oh, from there.
So I hope you can see that this leads into an issue of if you have to describe it as what's going counterclockwise if you're standing in the middle of the room facing the front. That's a whole lot. It would sure be convenient if we had a much faster way of describing the direction that was spinning. And there it is. You will use the right hand rule. So you notice that this has an axle to it. That is, well, it's bent a little bit here, but it's basically it's spinning as if there's an axle right along here. So in the right hand rule, again, not the dominant hand rule, it's the right hand rule. Your thumb is going to be the axle, which means my thumb is either going to point this way or that way. I want my fingers to curl in the direction in which it's spinning. So as it spins like this, well, if my thumb points towards the front of the classroom, my fingers are not curling the right way. My fingers need to curl the direction it's spinning. My thumb points at the back of the room. So the direction it's spinning is towards the back of the room. Now, when I was first doing physics and doing this, I got confused by that because I was thinking, all right, so what's going to the back of the room? Because I couldn't picture this thing spinning. This is just a mathematical convenience. So the way you determine the direction of spin so that you don't have to get into the, well, if you're standing here, it's clockwise. If you're standing there, it's counterclockwise. It's spinning towards the back of the room, which means that it is spinning, from your point of view, counterclockwise, from my point of view, clockwise. So, if it's spinning like this, what is the direction of the spin? You have to talk louder.
Is it to the
Up? Yes, it is. My thumb along the axle, which is now vertical, so my thumb points up or down, and my fingers curl in the direction that it's rotating. My thumb points up, it is rotating upwards. Obviously, we're now dealing with 3 dimensions. So if I hat is going to the right, J hat is up, then that last example, it was in the J hat direction. The angular velocity was in the J hat direction. However, the first example I gave would have been towards the back of the room, and so if I have an I and a J, well, K hat comes in next to do 3 dimensions, and K hat would be pointing to the back of the room. Now, to represent something going to basically a 3rd dimension, we of course need some sort of convention. So imagine if an arrow is being shot at you. You would see the point. So if it's coming at you, there'd be a point. K hat. That's it. If it's going away from you, you would see the feathers. Now I know arrow feathers don't look like this, but this is just a convention. And Levi, are you taking notes on the computer or doing something else? Okay. So this would be, the dot means out of the paper or out of the surface, out of surface. And the cross means in the surface. So if we close the door, what would be the direction, close that door, what would be the direction of the angular velocity?
Would it be up towards the ceiling?
It would. Because my axle are the hinges, which are vertical. So my thumb's pointing up or down, but the door's gonna be closing this way. That door will close this way. So up. Jay had given that convention. Now, it seems like I've used omega before to represent angular speed without the vector symbol. Let's talk about the conversions. We're about to double the number of formulas that we've worked with. Not scary, relatively simple. All right, so we start out with a different color. So if we're talking about velocity, I'll just do the vector versions. Sort of linear, or translational. Linear and translational are interchangeable. Typically I use linear, but if you hear translational movement, that's the same as linear movement. The symbol is a V. If we're talking about angular or rotational, we're not talking about velocity anymore, we're talking about angular velocity. And the symbol is an omega. Now, why is it called, why did I write angular velocity and not rotational velocity? Tradition. If you were talking to a physicist and you said rotational velocity, the physicist will know what you're talking about. If you say angular velocity, that's just what most people will call it.
Wait, how do you draw omega?
It looks like a curve W. Or potentially a body part. It is a lowercase omega. The uppercase omega. No, that's horrible. That's an uppercase omega. The uppercase one looks like a horseshoe. The lowercase looks like a curved W. At least today, it's a Greek letter. I don't know what the ancient Greeks did, because presumably they didn't have many curved lines. All right, if we're talking about displacement, we're talking about delta x, r, whatever. It's really angular displacement, although usually you don't see that wording. Angular displacement. Typically it's theta, phi is often used. Those are probably the two big ones. Alpha, beta, gamma are often used. I won't use alpha though, because we use that for something else. Oh, delta. And this is a theta, which I've definitely used in class before, and this is a phi. But typically in a problem, they'll just say the angle. I have an object spinning, through what angle does it turn? That's asking for angular displacement. acceleration. So want to take a wild guess what it's called over here when you're talking about the rotational version?
Angular acceleration.
Yep. And the symbol is an alpha. As you've noticed, we're using a bunch of Greek letters over here, and that's typical. It's not 100%, but typically, typical to be using Greek letters for rotational stuff. Let's see, so that's all chapter 3. Oh, we had one more thing from chapter 3, time. And the rotational equivalent of time?
Angular time.
It is not called angular time.
Wait.
What's that? When you think about the time it takes for something to go around, it's much simpler than you think.
What do you mean?
Just time. Yeah. Something going in a straight line or rotating, time's the same. So time stays. Let's see, chapter 1, we had force. The rotational equivalent of force is not called angular force, although I have seen that wording before, but typically it has a different name. Torque, symbolized by a tau. Now, I will also, and there are very few people who will get this reference, and I'm not going to explain the reference, but I also sometimes refer to torque as G2 kombucha. And pretty much the only people who will understand that reference are a handful of people from the late 70s and my students. Let's see, displacement, angular time, force, let's see, momentum. Which we used a P. All right, now we get back to the same, sort of the same pattern. What's the rotational version called?
Angular momentum.
Yep. And this is where they break the Greek letter bit. It's usually characterized by an L. All right, so I said we were going to double the number of formulas. Let's show how we're going to do that. Let's take a formula that we have dealt with before. Oh, I didn't do mass. Let's do mass first. I'm going to squeeze it in here. Mass.
Mass would be the same, right?
It is not. There is a rotational analog to it. Although, by my argument for time, it would make sense that mass would also, but there is it does matter how the mass is distributed. And they are in the other room. All right. The rotational analog of mass is called, has two names, either called rotational inertia or moment of inertia. And typically, if you see moment of something in physics or engineering, it means there's some rotation going on. The symbol for it is a capital I. So if I take Newton's second law, F equals ma, the rotational analog, there is a rotational version of this, and I just transliterate. Instead of force, I use torque. And Instead of mass, I use moment of inertia. Instead of acceleration, I use angular acceleration. If I've got a formula, sort of a hybrid, is in one of the videos, but if I have displacement is equal to the initial velocity times time plus 1/2 AT squared, this is basically Hewitt gives you that formula for acceleration is 0 and that formula if it starts at rest. But if we wanted to write this in for the rotational version of it, delta theta is equal to omega I t plus 1/2 alpha t squared. There was a look of fear back there. All right, let's show how you actually can use this stuff. Sorry, before we do that. Questions at this point? Before we do a problem? All right, first let's do a linear one. A rock is dropped near the surface of Earth. No, I'm going to change that. A car starts at rest and accelerates at 3 meters per second squared for 5 seconds. Put a little plus sign there to indicate vector acceleration. What is the car's velocity after 5 seconds? All right, so we have an object starting at rest. We can just use this equation over here. And it starts at rest, so the initial velocity is 0, so just displacement is equal to, oh, I asked for a different thing. I asked for final velocity. So final velocity is equal to initial velocity plus acceleration times time. That's, we pull that from the acceleration equation. But if initial velocity is 0, my final velocity is just acceleration times time. So my final velocity is just 3 meters per second squared times 5 seconds, or 15 meters per second. You also get the same thing by setting up the time. So I've got time 0, 1, 2, 3, 4, 5. Velocity starts at rest, and every second the velocity changes by positive 3 meters per second. So 3, 6, 9, 12, 15. That's a chapter 3 problem. Let's take a look at a chapter 8 problem. A wheel starts at rest and accelerates at plus 3 radians per second squared for 5 seconds. What is the wheel's angular velocity? It is the exact same math problem. Because instead of this equation right here, we have the equation omega final equals omega initial plus alpha t. That's 0 because it starts at rest, and so it's just the angular acceleration times time. And you end up with 15 radians per second.
Wait, so how do you show what direction it's going in? Like if it was like positive and angular, what direction would that be?
Well, I didn't define it. All I said it's in the positive direction. So, but if the wheel is spinning, as we talked about in the beginning, if the wheel is spinning from your point of view counterclockwise, the direction would be back of the room. From your point of view, if it was spinning clockwise, then front of the room. So it's not necessary to do more than just the positive direction, same like right here.
What would happen if like a problem had 3 directions?
Then more likely it's physics 151 or 251. You would still use I hat, J hat, K hat. Okay, we'll get to that when we talk about torque. There's no problems with 3 directions. I'm going to hold off for right now, if that works for you.
Yeah.
Okay. It's a 5, not an S. All right, so I have this unit of a radian. What is a radian?
Is it half the diameter of a circle?
Ah, that's radius. This is radian. It is related to the radius, but not that way.